Hello and welcome to this section of the chemistry tutor. In this section we're going to really roll up our sleeves and start to calculate what is happening in some of these chemical reactions. So the title of this section is called Reaction Stoichiometry. A lot of students get to this section or at least flip through the table of contents in a chemistry book and they'll see a giant word like stoichiometry and immediately get worried or freak out that it's just this really hard thing. You're going to have to trust me here. It is so simple, the method I'm going to teach you. You can calculate anything related to what a reaction is going to produce or what it's going to consume using some very simple tricks that I'm going to show you. And I've kind of laid the foundation for it, showing you how important that unit cancellation technique is, and here you're going to really see the power of it. Alright, so stoichiometry just means, in general, using a balanced chemical reaction to calculate what's basically going to form or really what's even been consumed. So you have to use the balanced reaction. That's why we covered how to balance reactions a minute ago. So anytime on a quiz or an exam or in a homework, if you're ever asked to calculate how much of something will form, either how many moles or how many grams, or how much of something was consumed in a reaction, you have to use the balanced reaction. So double check to make sure that it's balanced, and if it's not balanced, then you have to balance it yourself before you can do any calculations related to what's been formed. All right? So the easiest way to show you how easy stoichiometry is to show you. So let's do that here. Let's look at a chemical reaction. Let me just write it down. This one's already going to be balanced. C3H8, which is propane. You've probably heard of propane before, plus 5O2, that's just adding oxygen, yields 3CO2, carbon dioxide, plus 4H2O, so 4 moles of water. This is already balanced. You should always verify that it is, though. 3 carbons, 8 hydrogens. You have 2 times 4 is 8 hydrogens, 10 oxygens, and here you have 6 oxygens. 2 times 3 is 6, plus another 4 gives you 10 oxygens. So this guy is balanced. Now the problem says, how many moles of carbon dioxide are formed when 0.529 moles of C3H8, which is propane, is burned? Because this is a burning reaction. You're taking some propane, you're putting oxygen with it, and the way you get that to happen is you light it on fire and they combine, and then you get carbon dioxide plus water. By the way, almost anything you burn is going to produce CO2 plus H2O, carbon dioxide plus water. Almost always that's what's going to come out of any kind of combustion reaction, especially the kind that you'll study in Chemistry 1. All right, so how many moles of carbon dioxide are formed when we consume 0.529 moles of this propane? So this is a great example. It's very simple, but if you don't know how to set it up, you're wondering, what do I do? Well, I have the reaction here. I know how much I've used of this propane. Where do I start? Let me show you the bulletproof way to do all of these problems, all right? So pay attention, because we're going to do this over and over again. What you do is you write down what you know. You always write down what you know. What we know is we have 0.529 moles, and don't just put moles down. You have to say moles of, what are you talking about? Moles of C3H8. And I draw my horizontal line, and I draw my vertical line. What we're going to do is a unit cancellation here. This is one of the first things I taught you in chemistry, and this is why it's so important. What we need to do is come up with a conversion factor. What we're trying to end up with is moles of carbon dioxide. Moles of carbon dioxide. But we need to know how moles of carbon dioxide are related to moles of this propane, because that's what we started with. So how do we get that? We get it from the reaction. We know that for every 1 mole of this propane, 3 moles of carbon dioxide are produced. This is the magic ratio. 1 mole of propane for every 3 moles of this stuff is produced. So if I shovel another mole of propane in there, I should get another 3 moles of this out. If I take another shovelful and throw another shovel of propane in there and burn it, I should get another 3 moles of this. So it's a ratio. It's telling you every time you dump another mole of propane in, you should get 3 moles of carbon dioxide out. That is the importance of these coefficients here. And notice in the last section we actually called them the stoichiometric coefficients. They're telling you how these things combine. So the way you actually solve the problem is you need to write a conversion factor. The way I'm going to write it is 1 mole of C3H8 is a ratio, or locked in because of this reaction, to 3 moles of CO2. Now anytime you write one of these conversion factors, you have the choice of flipping it either way you want. I could have written moles of C3H8 on top and moles of CO2 on the bottom, but doing that wouldn't have done anything for me because you want to cancel the units. Moles of C3H8 cancels with moles of propane down here, and that's gone. The only thing you have left unit-wise is moles of carbon dioxide, which is exactly what I'm trying to find. How many moles of carbon dioxide are formed? So it's as simple as that. You take 0.529, you multiply it by 3, and then you divide by 1, because the 1 is on the bottom. Of course, dividing by 1 doesn't do anything. So you literally take 0.529 times 3 divided by 1, and when you do that, you get 1.59 moles of CO2. And this is how many moles are produced. So that's the way you do all these problems. You write down what you start with, you find a ratio from your reaction to cancel units, and the unit that you're left with should be what you're trying to find. That's the game that you play. In this case, we take this times 3 divided by 1, we get 1.59 moles of carbon dioxide. Okay, so for the next problem, we're going to use exactly the same chemical reaction. I'm going to do a few of these problems with the same reaction so you can get a feel for basically what you're doing, so I'm not changing too many things on you at one time. So the next problem says, given again this reaction, which is balanced, we already discussed that, how many moles of water are produced when 76.2 moles of C3H8, which is the propane, is burned? So how many moles of water are produced when 76.2 moles of C3H8 is burned? So we have a new starting point, but exactly the same logic flows. So again, start by writing down what you already know. So now, in this case, we know that we have 76.2 moles, but don't stop there. You have to specify when you do this conversion factor stuff, you have to specify what you have. So 76.2 moles of C3H8. All right, now we basically want to convert this using our balanced chemical reaction. All right, now we want to go from moles of C3H8 to moles of water. So in this case, you can sort of look from the reaction and see that for every 1 mole of propane that we have here, 4 moles of water is produced. So that's a different ratio from before. From before, for every mole of this, we produce 3 moles of carbon dioxide, so that's why we use this. But in this case, for every 1 mole of this, we produce 4 moles of water. So the conversion factor is going to be different. So we'll write down 1 mole of C3H8 for every 4 moles of H2O. And this is why it's so very, very important to write down what you're talking about. In this case, it's moles of C3H8 because this one is going to cancel with this one. Now, when you're constructing these things, again, you can flip them around any way you want. You just need to get the cancellations that you want. The guy on the top canceling has to cancel with something on the bottom. So in this case, the only unit left over is moles of water, which is what you actually want. So in this case, the way to get the answer is you take 76.2, multiply by 4, and then divide by 1. So when you actually do that, multiply by 4, divide by 1, you'll get 305 moles of H2O. Now this is such a much larger number than what we got before for 2 reasons. Number 1, we started out with a whole lot more propane. See, in this case we had less than a mole of propane we started with. Now we're starting with over 76 moles. So we expect to produce more products because we're starting with more reactants on the left-hand side. And on top of that, for every 1 mole of propane that we use, we actually are producing more water than in this particular calculation. So for those 2 reasons, even though it's similar logic, we actually get more water produced than carbon dioxide. All right, so basically the trick to all of these problems, we're going to do a few more in this section, and then in the next section we'll have some different problems. But the number 1 thing I need to impress upon you early on is don't worry, don't get too stressed out about this stoichiometry stuff. What you need to do in every single case is write down what you know, and you are free to pick these conversion factors from your reaction. Sometimes you'll have to use the periodic table if you're going from moles to grams, for instance. But the magic key that lets you calculate products and reactants comes from the reaction and the coefficients that are in front of all of these guys. Those are the golden ratios, so to speak, that govern what's going to actually be used and what's going to be produced. So let's take another guy. We've done these 2 guys. Now let's go ahead and use exactly the same reaction again and do another one. This one says, how many moles of carbon dioxide are produced when 1.010 moles of oxygen are consumed? All right, so it's almost exactly the same logic. It's just in the previous two problems, we were given how much propane is consumed, and we're calculating some products. But now I'm going to show you that it really doesn't much matter where you start. This problem says how many moles of carbon dioxide are produced when we have so many moles of oxygen. So we're going to start with that. Now we start exactly as we always have been. We write down what we know. So in this case, we have 1.010 moles of oxygen, right? That's what we start with. And then we need to create a conversion factor. We're trying to figure out how many moles of carbon dioxide. So we know for every 5 moles of oxygen, 3 moles of carbon dioxide are produced. Let me say that one more time. For every 5 moles of oxygen, 3 moles of this carbon dioxide is produced. So these two are the magic numbers that link how these two things are related in this reaction. So we want to go from moles of oxygen up to moles of carbon dioxide. So the way you would write it is 5 moles of oxygen is basically locked in ratio-wise with 3 moles of CO2. And the reason we're writing it this way instead of flipping it upside down is because we want moles of oxygen to cancel with moles of oxygen on top and bottom. So what you have is, the only unit left in the end of the day is moles of carbon dioxide, which is exactly what you're trying to calculate. So to get the answer, you take 1.010, multiply by 3, and then divide by 5. So basically you just keep multiplying and dividing. You may have more conversions out here as we get to more complicated things later on, but in every case you multiply by the numbers on the top, you divide by the numbers on the bottom. So in your calculator, 1.010 times 3 divided by 5, you should get 0.606 moles of CO2. Let me just circle these guys here. So I'm trying to show you a pattern. I'm using exactly the same reaction. In the first two cases, we were given an initial quantity of this and asked to calculate individually how much of these things are produced. In the third one, you see, if you're not using this unit conversion method, you might think that this is a totally different problem because we're not given this guy, we're given this guy. But I'm showing you logically that you just write down what you start and you use the ratios in the reaction to cancel and you get what you want out. And you don't have to think at that point. I hate to sound like that. I mean, I want you to always think, obviously, and understand what you're doing. But if you don't use this technique, then you're constantly going to be having to think, should I multiply by 3 and divide by 5, or should I multiply by 5 and divide by 3? And that's really confusing for a lot of students. But when you use this technique, you don't have to worry about that part of it. You just arrange the conversion factors in such a way that you always get what you want. And that's going to be bulletproof every single time. So it's very, very powerful, very, very important. All right, now let's go and do a different reaction, a slightly different reaction, and we'll ask ourselves something here. So we have, in this case, octane, right? You've heard of octane, right, in relation to gasoline. C8H18, we have 2 moles of octane plus 25 moles of oxygen yields 16 moles of carbon dioxide plus 18 moles of water. So this is a different reaction. So this isn't propane, this is octane, right, because of the 8. And we're burning it with tons of oxygen, excess oxygen. So that's what we're burning, octane and excess oxygen. And then as a result, we get CO2 plus H2O. And these are the stoichiometric coefficients, the magic ratios. So we know from this reaction, for instance, that for every 2 moles of this octane, we're going to produce 16 moles of carbon dioxide. We know that for every 25 moles of oxygen, we're going to get 18 moles of hydrogen, or of water. We also know that for every 25 moles of this, we get 16 moles of this. So the question says, how many moles of oxygen are consumed in the combustion of 4.4 times 10 to the 4 moles of this octane? So we're asking ourselves, we're given how much octane, which is the fuel, we're starting with, and we're asked how much oxygen is being consumed. And so this is the reaction here, and we know the ratio. We know that these guys burn in the ratio of just a little bit of octane, and it takes a whole lot of oxygen to combine with it, because for every 2 moles of octane, we actually require 25 moles of oxygen to even do this reaction. But again, you just write down what you know. And what we know now is the starting point, 4.4 times 10 to the 4 moles of this octane, C8H18. Okay, so this is a large number of moles, times 10 to the 4. That's thousands of moles of this guy here. We're asking ourselves, how much oxygen is consumed? So you don't get too worried about that. I mean, this is carbon dioxide. This is not oxygen. This is water, so it's not pure oxygen. The only thing that's really pure oxygen is this. So we know that ratio, and so we need to write this guy here. So we know that for every 2 moles of C8H18, the reaction is going to require 25 moles of oxygen. And the reason we arrange it this way instead of flipping it over is because we have to have the moles of octane on the bottom, so they'll cancel with the moles of octane up here. So now it's very, very simple. You take 4.4 times 10 to the 4 in your calculator, multiply it by 25, and then once you get that, you divide the result by 2. And so what you get when you do that is 5.5 times 10 to the 5 moles of oxygen. And that's the result. The reason it's moles of oxygen is because that's the only thing left over unit-wise. So in other words, you start with a ton of this octane and you burn it with oxygen, and given the ratios here, you end up basically with a ton of oxygen required to do that. So I tried to give you a few examples to show you how to do this. Basically, the main thing I want to get across here is it doesn't really matter where you start in the reaction and what you're trying to calculate. It doesn't matter if you have something on the right-hand side of the equal sign and you're trying to calculate something on the left-hand side, or if it's something on the left and you're trying to calculate something on the right, or if it's something on the left and you're trying to calculate something else on the left. It doesn't matter. Only those coefficients matter. In every case, you write down what you have and you pick a conversion factor based on this reaction to give you moles of what you're trying to get. Same thing here, same thing here. Everything was the same in all cases. The number one thing that I can tell you, like if I had to pick one trick out of chemistry to tell you, in fact in all of chemistry, if I had to pick almost one thing to tell you that will really help you, is when you're writing these conversion factors and figuring out what to do, be very explicit. A lot of students, when they see the problem, they'll write 4.4 times 10 to the 4 moles. They won't write this. And then they'll come over here and they'll write 2 moles and 25 moles. Well, see, then you get confused. You cancel moles and moles, and if you haven't labeled what moles you're talking about, then you're not going to be sure what your answer is. In this case, it's not as hard to keep track of because we only have one conversion factor. But in future problems, when we start tacking on a lot of conversion factors, for instance, what if we didn't want moles of oxygen? What if we wanted grams of oxygen? Then we would have to go to the periodic table and find out how many grams were in every mole of this oxygen molecule, and we'd have another conversion factor here to cancel and give us grams, right? But if you don't label everything explicitly, grams of oxygen, moles of octane, moles of propane, if you don't label it explicitly, then you're going to get confused with what you're canceling and you're not going to know what your final unit is supposed to be. So be explicit. If you're talking about moles of this stuff, write it down. If you're talking about later on liters, like if you're talking about volume, liters of this gas, write it down, liters of oxygen. If you're talking about something else, make sure that you're labeling it accordingly so that when you do this and use these conversion factors, you won't get lost. So let's go and wrap it up here. Work these, make sure you understand how they were done, make sure you fully understand the technique. It's so incredibly powerful using this method here. In fact, we're going to be using this method almost in every section from here on out because it's so powerful. And a lot of books dance around it. A lot of books don't teach you quite how incredibly important it is. If you can master this concept of canceling and just kind of using your conversion factors, you will go as far as you want in chemistry because that's really, honestly, the secret of doing well in that class, in my opinion. Let's wrap it up here. In the next section, we'll work some more stoichiometry problems, a little bit more involved in the future problems, but again, nothing is more, big picture, nothing is more complicated than what we're doing here, just a little bit more steps in the next lesson.